Let's start off with the definition of a continuous function f at a point A. So the limit as x approaches a of f of x is equal to f of a. So from this we require three things. First is that the function is defined at that point A, the limit at that point needs to exist, and that the value of the limit and the value of the function at that point are equal. So when these are satisfied, then the function is continuous at a point A. And we say that a function is continuous on an interval if all points on that interval satisfy this property. So for our first example, let's look at this function, f of x equals x squared minus x minus 2 divided by x minus 2. Is the function continuous at x equals 2? Well, if we plug in 2, then the denominator will be 0. So this function is undefined at x equals 2. So therefore, f is not continuous at 2. Now let's ask the same question but for this function. This function is a piecewise function. When x is not equal to 2, we use this expression. And if x is equal to 2, then the value of this function is 3. So f of 2 is 3 because we're defining it that way. Next, let's try to compute the limits. So what's the limit as x goes to 2 of this? We need to algebraically manipulate this. We can factor the numerator into x plus 1 times x minus 2. And in the limit, these will cancel. So this becomes the limit as x goes to 2 of x plus 1, which is 3. So we have that the limit as x goes to 2 is equal to f of 2. So it is continuous at x equals to 2. Graphically, the first function, just this expression, was this line but with a hole in the middle. So it was not defined at 2. And then we filled in the hole by defining by the correct value. And then it becomes continuous. Now if we plug in a different value, then the function will not be continuous because the limit will still be 3. But if the value that it's assigned to is not 3, then it's not continuous. Most, if not all, of the functions that we will talk about in this course will be continuous. So here, functions which are continuous on their domain. So for example, where is this function continuous? Well, we just need to find the domain of this function. From here, we know that x needs to be greater than or equal to 0 because we can't plug in negative numbers to a square root. And here, x cannot equal 1. So the function is continuous for all numbers between 0 and 1, strictly less than 1, and numbers strictly greater than 1, and finite numbers. Another way to write this in interval notation is like this. So inclusive, we have a square bracket, and exclusive, we have a rounded out bracket, or parentheses. One important theorem concerning continuous functions is the intermediate value theorem. So here it is. So given a continuous function on an interval, if we pick a number between f of a and f of b, then there must be a number between a and b such that f of, let's say, c is equal to this number. So visually, something like this. Suppose we have a function f of x given by this graph. Then we can pick any number between f of a and f of b. For instance, let's say this number here. It's between here. Then there is a number between a and b such that f is equal to this number. So that's not too hard to see. This number here, because f of c will be equal to capital N. So how can we use the intermediate value theorem? Well, here's one use. Suppose we have a polynomial p of x, then we want to show that there is a root, the numbers 1 and 2. But that's not too hard to do. We simply evaluate the polynomial at 1, which will be negative 1, and then we'll evaluate at 2, which if you plug in, you'll get 12. Well, notice that p of 1 is negative, P of 2 is positive, so 0 is a number between a negative and a positive number. By the intermediate value theorem, there is a C between 1 and 2 such that P of C equals 0, which is a root. So here's one way that we can apply intermediate value theorem to show that there exists a root. It might make sense to first know that there exists a root before we try to find a root. Remember, this is a cubic, so it's quite difficult to try to find a root. So if you want to use a computer to try to approximate it, well, you want to make sure that there is a root there to begin with.